Swayam Prabha. Digital India. Educated India.
It is my privilege to introduce Professor S. Sankara Raman. He has 25 years of teaching and research experience in IIT Madras. He teaches theory courses on organic chemistry, organometallic chemistry, spectroscopy, and photochemistry to MSc and PhD students, in addition to teaching basic organic chemistry and in basic and organic and inorganic chemistry courses to BTech students. It's my privilege to have you here, sir.
Thank you. Good morning, all of you. To introduce you to a spectroscopic technique called nuclear magnetic resonance spectroscopy. This is one of the most important spectroscopic technique if you are an organic chemistry student, research student, because organic chemists heavily depend upon the NMR spectroscopy for structure elucidation of organic compounds. So when I say structure elucidation here, specifically organic compounds is what we mean in the spectroscopy. And also this is the least sensitive of all spectroscopic techniques. You will be surprised how the spectroscopic technique is very weak, and yet it is highly useful in research. You might have heard about nuclear magnetic resonance, not spectroscopy but imaging. This is again a spectroscopy kind of a technique only. You look at water molecules in the human body at various locations and map the different types of water molecules in the NMR spectroscopy deals with nuclear spin. Nuclear spin has something to do with the magnetic property of the nucleus, and historically the credit is given to Purcell and Bloch, the two scientists, one from Harvard and another one from Stanford University, for describing the phenomena of NMR spectrum, NMR phenomenon. What they did was essentially take a laboratory magnet and put ethyl alcohol in between the pole pieces of the magnet and start irradiating with electromagnetic radiation. When they came to the radio frequency region of the electromagnetic radiation, they could see it is being absorbed by the sample. And otherwise, if you turn off the magnet, there is no absorption of electromagnetic radiation. So this has something to do with the presence of a magnetic behavior of ethyl alcohol in the sample, right? This is the first ever published NMR spectrum of ethyl alcohol. This is supposed to be a high resolution in those days, but today high resolution has a totally different connotation and meaning. You can see three peaks in this spectrum. Ethyl alcohol has CH3, CH2, OH. So CH3, 3 hydrogens come separately, CH2, 2 hydrogens come separately, and OH hydrogen comes separately. In fact, if we integrate the area under each of these peaks, you will get 1:2:3 ratio corresponding to the CH-OH, CH2 and CH3 of ethyl alcohol. Structure elucidation is possible even in those days when the resolution was very poor. We are dealing with the magnetic property of the nucleus. Nucleus has spin. Nucleus has a spin of on its own axis, and because of the spin, it has an angular momentum. any mass which is spinning mass will have an angular momentum. And because it is a charged particle, it will also have a magnetic moment. A charged mass will have magnetic moment as well as angular momentum. And this is what is fundamental property of the nucleus. Due to the charge and the spin, it possesses a magnetic momentum. Only certain nuclei have a non-zero magnetic moment. Others, net magnetic moment can be zero. It is essential that the nucleus has a magnetic momentum. Otherwise, it is useless in the NMR spectroscopy technique. Only nuclei have non-zero magnetic moment, can be magnetically active and hence useful in NMR. Both P and Q are vector quantities. The ratio of the magnetic moment to angular momentum is called gyromagnetic ratio. This is a God-given property of the nucleus, and only those nuclei which have a non-zero gyromagnetic ratio is useful in the NMR spectroscopy. These are some websites where you can find out about the magnetic properties of the elements. Bruker has a page of its own. And here what you have is proton, deuteron, and tritium. The three isotopes of hydrogen are given here. The natural abundance of proton is 99.98, whereas deuterium is 1.5 10 to the power minus 2. Tritium, of course, has no natural abundance because it is a synthetic element. The spin is half, 1, half. The gyromagnetic ratio is given here. And the quadrupole moment, which is not relevant to NMR spectroscopy, is given here. Resonance frequency with respect to the nucleus. Sensitivity of the technique with respect to 500 megahertz NMR spectrometer is given there. According to quantum mechanics, angular momentum and have only certain fixed value, eigenvalues. That is, angular momentum is equal to magnetic moment times h by 2 pi. In the presence of an external magnetic field, a magnetic moment has values 2i plus 1 value. 2i plus 1 value corresponds to plus i2 minus I, where I is a spin quantum number, right? This is very similar to the electron configuration you normally deal with. A spin of half can have two possible orientation. One is aligning with the external magnetic field, other one is opposing the external magnetic field. This property you can measure only in the presence of a magnetic field, right? Magnetic property can be measured only in the presence of an external magnetic field. When I is equal to 1, three states are possible: plus 1, 0, minus 1. These are the orientations of the spins. The spin of 1 has orientation minus 1, 0, plus 1. Spin of half has orientation of minus half and plus half in the presence of external magnetic field. A simple way to remember the spin of a nucleus is as follows. If you have a atomic mass and atomic number, if you know, if both of them are even, then spin is 0. For example, carbon and oxygen 16, carbon 12, oxygen 16 have spin of 0. So they are not useful in the NMR spectroscopy because they are not magnetically active. When the atomic mass is even and atomic number is odd, it is an integer multiple is what they have. Integer multiple, nitrogen 14, boron 10, deuteron, these are the nuclei which are having a integer value for the spin half is atomic mass is odd and atomic number is odd or even, multiple of half. So proton, carbon 13, nitrogen 15, boron 11, these are nuclei which have the spin of half integer. Proton, carbon 13 for example have a half spin half. These are some properties of the nuclei which we deal with in the organic chemistry laboratory. Proton, carbon 13, fluorine, phosphorus and silicon. These are the nuclei which we deal with in the laboratory. And these are the spin value of the nuclei, gamma value of the nucleus, and abundance of the nucleus in the nature. You can see some of the nuclei have 100% abundance. For example, fluorine and phosphorus 31. Proton has almost 100%, 99.9%. The higher the abundance, the more sensitive the technique is, right? In the presence of an external magnetic field, the magnetic moment vectors will be randomly oriented, and in the presence of a magnetic field, they will have the orientation dictated by the spin of the nucleus. The two orientation, one aligning and one opposing the external magnetic field, differ in energy. The energy difference depends on the strength of the applied magnetic field. So this is the area where you have a random orientation of the spins. They don't have any particular orientation. This is in the absence of magnetic field. So once you apply the magnetic field, there is two states are there. One state is aligning with the external magnetic field. This is opposing the external magnetic field. These two states are there, spin states are there. We are dealing with the nuclear magnetic resonance spectrum, and this is a transition which is responsible for the signal that you get in the nuclear magnetic resonance spectrometer. Now here, with the increasing field strength, you see that the energy gap increases. In other words, the energy gap is directly proportional to the applied magnetic field. Larger the magnetic field, higher will be the gap between the ground state and the excited state. In normal spectroscopic terms, you will call this as a ground state and this as an excited state. But here you call it as a spin half, spin minus half and plus half, or beta or alpha states of the nucleus. One can calculate the population difference between the ground state and the excited state using the Maxwell's equation. Maxwell-Boltzmann distribution tells you how much excess population is present in the ground state compared to an excited state. Is the population ratio of the excited state to ground state, n alpha by n beta. That is equal to exponential time minus delta E kT. KT is Boltzmann's constant, T is temperature, and delta E is the energy gap between the two states according to the. If you keep increasing the magnetic field strength, applied magnetic field strength, the gap increases between the alpha state and the beta state. And accordingly, the magnetic field strength dictates the radio frequency to be used for the excitation of the sample. This is the delta E, which is the difference between the two states. I am talking about difference between the two states here, this state and this state, as delta E. So, higher the magnetic field strength, higher is the sensitivity of the NMR. Lower the temperature, higher the sensitivity of the NMR spectrometer. The energy gap between the alpha state and the beta state lies in the radio frequency region of the electromagnetic radiation. Application of radio frequency causes the same absorption of the same due to the excitation of the nuclear spins from lower energy state to upper energy state. When the energy matches, you have a resonance condition, right? With the increasing field strength, the B0 increases, the laboratory magnetic field strength increases, the energy gap increases. Once the energy gap increases, the population difference also increases, right? There will be more alpha state than beta state and so on. This is a classical description of NMR. So far we have been looking at the quantum mechanical description of NMR. The classical description of NMR is as follows. The interaction of magnetic field with the nuclear moment induces the nuclear magnetic moment to process about the applied magnetic field. This can be better explained in the form of a diagram. This is a spinning nucleus. The spinning nucleus has angular momentum. As a result of that, the spinning nucleus spins at a distance of theta with respect to the mu, which is the magnetic moment vector. And this precision frequency is what is known as the Lamar frequency, and that is corresponding to the transition energy between alpha and beta state. Once the spin is in the excited state, it doesn't stay there forever. It would like to come back, and it will come back by means of two mechanisms: spin lattice relaxation and spin-spin relaxation. Spin lattice relaxation means it is dissipating the energy to the surroundings, to the solvent and so on. And spin-spin relaxation means it is dissipating the energy to another spin system in the solution. From proton to carbon-13, for example, one can transfer the energy. Now, the concept of chemical shift is important. Now, the frequency is directly proportional to applied magnetic field strength as well as gamma. Higher the gamma, the better the sensitivity. Higher the field strength, the better the sensitivity because of the population difference. So, the frequency is directly proportional to B0 gamma by 2 pi. This would mean all the protons in the earth or elsewhere will have the same frequency, because B0 is applied magnetic field strength that is within your reach. It is a laboratory magnet is what is being set up, and gamma is a gyromagnetic ratio, which is a God-given property of the nucleus. You cannot do anything about it. So, these two are constant, and this is of course a constant. So, the whole thing is a constant. The frequency, one frequency is what you will observe for the entire population of protons. But this is not true. So, if this is a true, and then the nuclear magnetic resonance spectroscopy would not have existed. So, hydrogen is different from the environment, chemical environment, given different resonance frequencies in the NMR. We have already seen the proton has 3 different hydrogens, and 3 different hydrogens give 3 different peaks in the NMR spectrum. This is a spectrum that we saw. And this is a modern spectrometer spectrum. You can see how different it is in terms of the sensitivity and the resolution that you have here. The resolution particularly is terrific here. You have a singlet in the OH region, methylene quartet, and a methyl triplet is there. Now we will see how the splitting happens in the spectrum. In chemical systems, nucleus is not isolated entity. It is always surrounded by electrons. And electron is a charged particle and it has its own spin. So it will produce its own magnetic moment. And the induced magnetic moment due to the electrons will oppose the external magnetic field strength. And the external magnetic field strength is not what you apply. It does not feel the B0, but B effective is what it feels. In other words, there is a mechanism by which the electron is going to shield the nucleus from the external magnetic field. This is what it implies. And sigma is the shielding constant, chemical environment of the proton. So depending on the electron density, you will have different electron density around different hydrogens. So the sigma will be different for different hydrogens. And as a result of that, you have different frequencies for the different hydrogens in the molecule. So now NMR spectroscopy is more meaningful if you have different frequency for different types of protons in the NMR spectrum, then structural elucidation becomes easier. The chemical shift is a output of the NMR spectroscopy, and this is essentially, you don't like to, you have fractional numbers like this 398.432 and so on. Instead of that, actual frequencies of resonance are taken. Frequencies are calibrated with respect to a sample, standard sample, and divided by the spectrometer frequency to normalize the value. This is a sample you measure. The frequency of the sample you measure minus the frequency of the resonance times spectrometer frequency. This is quantity in hertz. This is a quantity in megahertz. So a factor of 10 to the power 6 is added, so that you have a dimensionless quantity in parts per million, expressed in parts per million. The chemical shift expressed in delta is a dimensionless quantity, also do not depend upon the spectrometer frequency. So if somebody is measuring a spectrum in a 500 megahertz NMR spectrometer here, and the same sample is measured elsewhere and on 200 megahertz NMR spectrometer, you will get essentially the same spectrum, but the sensitivity will be different for the different spectrometers. Now tetramethylsilane is used as a standard sample in the NMR spectrum. Chemical shift of a tetramethylsilyl group is lowest in the NMR spectrometer. So it is taken as 0. All the protons are equivalent. What do you mean by equivalent is they have same chemical environment, tetrahedral complex. TMS is a liquid and it is miscible with most organic solvents. It's also volatile and hence easy to remove. It is inert and does not react with any sample, your sample. So the NMR spectrum with the TMS standard is more useful than the for example, if you want to scan 10 ppm of spectrum at 60 megahertz NMR spectrometer, you would be scanning 600 hertz width of the NMR spectrum. Similarly, when you have a 400 megahertz NMR spectrometer, to the same 10 ppm width, to scan, you have to scan 4,000 hertz NMR spectrum. This essentially tells you the spread of the NMR spectrum with a higher frequency. So, as a result of that, you will have better resolution. What are the factors that affect the chemical shift values of the samples? Take for example, tetramethylsilane is taken as 0 and methyl iodide is 2.2, methyl bromide is 2.6, methyl chloride is 3.1, methyl fluoride is 4.3. What is changing among the samples? The halogen is changing. How is it changing? Go from iodide to fluorine, you become more and more electron negative, right? That means the electron density around the fluorine will be it is the electron withdrawing nature of the fluorine that is going to affect the electron density around the methyl group. Methyl group will have a lesser electron density, right? So, methyl group having a less electron density will be at a higher frequency, 4.3. This is also an additive property. You have methyl chloride, dichloromethane and chloroform. As you increase the number of chlorine atoms, the electron density on the carbon hydrogen bond is going to be weaker. So, as a result of that, you have a higher delta value coming in the frequency in the here methanol, methyl fluoride and nitromethane, methyl fluoride and nitromethane have the same chemical shift value, indicating that their electron withdrawing nature is about the same. So, oftentimes you use the chemical intuition to follow the chemical shift value. If we take ethylene, it is a symmetrical molecule. It will have only one peak in the NMR spectrum, and that will be coming around, let us say, 5 ppm or so. I put an aldehyde substituent. Aldehyde is an electron withdrawing functional group in organic chemistry. So, this will have an effect on the CH hydrogen as well as CH2 hydrogen because of the electron withdrawing nature of the aldehyde functional group. If the electron withdrawing nature of aldehyde functional group is going to affect the CH and the CH2, how is it going to affect? Which one is going to come at a higher delta value? You have less electron density in the beta carbon compared to the alpha carbon, like that. So, the beta carbon hydrogen will come at a higher delta value compared to the alpha hydrogen of the acraldehyde. Now, anisotropic effect is something which has to deal with the non-spherical distribution of electron density around the molecule. Spherical electron density means induced magnetic field will be uniform in space and isotropic in nature. For example, S electron is spherical in nature, but you don't have S electron, pure S electron in the molecules. You have only hybridized systems like carbonyl and olefin and so on. Non-spherical electron density means induced magnetic field will be non-uniform in space, and anisotropy is a cause of that. For example, pi electron clouds of aromatic ring, it's not spherical. Carbonyl group doesn't have spherical electron density. So these are the most common features of the organic molecule. The external magnetic field is applied in this direction. With respect to that, the olefin has two regions. One is a shielding region, the other one is a de-shielding region. Shielding region means it is shielding the external magnetic field from going to the nucleus. De-shielding means external magnetic field is not going into that. So these are the zones of the anisotropic effect in the organic molecules. Benzene, for example, is a flat molecule. It has a pi electron density around it, and the pi electron density will be like a donut shaped in the top and bottom, right? It's sandwiched between two donuts is the picture you draw normally. So here what you have is the peripheral hydrogens will have a higher delta value. The internal hydrogen, if at all there is a hydrogen in the internal of the, will have a lower delta value. This is a shielding zone and this is a de-shielding zone. The carbonyl peak also, the shielding and de-shielding zones are marked here. And accordingly, for example, the aldehyde hydrogen comes at a very high delta value, 9.1. These are some aromatic compounds, not benzenoid compounds. Benzenoid compound, this has a 10 pi electron, it's aromatic, 10 pi electron, right? So you can see here, this is 7.29 and this is coming above the pi electron density, which is minus 0.51. Here, for example, it is minus 4.2 is the internal methyl hydrogen. This molecule is going to look like this in reality. It is a flat molecule with one methyl up and one methyl down. These two molecules. The peripheral hydrogens have 8.4 to 8.67 ppm. The internal hydrogen, which is a methyl hydrogen, which are these hydrogens, comes around 4.2 ppm or so. This is a 18 aniline system. 18 aniline system has 6 hydrogens which are inside, 12 hydrogens which are outside the ring. The interior of the ring is de-shielded, highly shielded. The exterior of the ring is highly de-shielded, 9.3 and 3.0. These are some cyclohexane molecule to illustrate the point that anisotropic effect can come from carbon-carbon bond, which is this bond here. Anisotropic effect of the sigma bond causes the shifts of the molecule. Ethyl alcohol spectrum now, for example, this is a quartet and this is a triplet. Why is it a triplet and a quartet? Here, the adjacent proton makes a difference. If you have only one proton and there is no other proton to interact with this system, it will have only one peak, right? Absence of any interaction proton, neighboring proton, no spin-spin coupling, only single peak will be each chemically different protons. This is a non-interacting system. The beta, alpha states are clearly marked here. This is a beta state going to alpha state. This is a beta state going to alpha state. This is a beta state going to alpha state. There are two peaks, but they are equal energy because there is no spin-spin interaction between them. So if they are equal energy, they will give one peak. This is a smaller frequency. Again, the energy is same here. So it will give one peak which is different than the other peak. But there is no spin-spin interaction between the two. So you will give only two peaks in this spectrum. Here there are 4 peaks, 4 transitions are possible. 1, 2, 3, 4. All the 4 transitions are different in energy. So you will have 4 peaks in this particular spectrum. When there is a spin-spin interaction, what happens is alpha to beta state is a transition for HA, when HA is in the alpha state and HB is in the beta state. So this is something which causes the spin-spin splitting of the NMR spectrum. Here alpha to beta state, when HA is in alpha, HA is in alpha, HA is in beta, HA is in beta. So these are the 4 lines you will get in the NMR spectrum for the same thing I am explaining again. Here there are no coupled hydrogens in the adjacent position. Here there is 1 coupled hydrogen, 2 coupled hydrogen, 3 coupled hydrogen. So 1 coupled hydrogen means it is a doublet and doublet. You see a doublet for one of the hydrogens. This is 2 coupled hydrogens means triplet. 3-line pattern is what you see. This is a 4-line coupling is because of the quartet that you get. What is a quartet due to? If there are 2 hydrogens, alpha alpha state, alpha beta state, beta alpha state. This is a transition which is observed, and this is a spin-spin coupling partner which is in the spin state of alpha alpha, alpha beta or beta alpha. It's as if you have a tiny little magnet in the form of a proton sitting next to the other proton, causing the spin-spin splitting to happen. Here again, the coupling partners are specifically mentioned here. JA is split into JB, JB is split into JC. So these are the coupling partners of the olefinic hydrogens. Spin-spin coupling constant depends on distance between the coupling partners, intervening bonds, dihedral angle between the coupling partners. Coupling constant is large when the dihedral angle is 180, small when the dihedral angle is 90. In freely rotating alkyl chains, average J value is obtained. This is called the Karplus equation, and this they calculate the J value with respect to the theta, which is the dihedral angle here. The number of lines from coupling is corresponding to 2Ni plus 1. N is the number of protons, equivalent protons adjacent position. I is the spin quantum number of the. So, for I is equal to half, you will have N plus 1 protons, N plus 1 signals splitting in this particular case. This is what makes it useful in the NMR spectrum for the structural elucidation process. You are converting the spectral pattern into molecular dimension here. For example, if you have a ethyl group, you will have a triplet and a quartet. Triplet for the CH3, quartet for the CH2. You have adjacent for 3 hydrogens, so you will have 4 lines pattern in the spectrum. Adjacent 2 hydrogen will have 3 line pattern in the spectrum. Here, for example, 3 plus 2, 5 hydrogens are there. So, sextet is a signal you get in this particular case. Sextet because 3 plus 2 is 5, 2Ni plus 1 is equal to 6. So, that is the reason it gives this. The signal intensities are predictable, corresponding to the coefficients of binomial expansion, can be obtained simply from Pascal triangle. This is for singlet, doublet, triplet, quartet, quintet and sextet. This is the kind of intensity ratios you get, for example, in the spectrum. The different electron density causes the different hydrogens to have different chemical shift value in the NMR spectrum. This is a chart of the chemical shift value. Chart of the chemical shift value with respect to structure. For example, alkane hydrogens come in the region of 1 to 2. Saturated alkane, for example, comes in the region of 1 to 2. Monosubstituted derivatives come from anywhere from 2 to 334. From monosubstituted alcohol, nitro compound, esters, bromine, halogens, for example, they all come in this region. Amide hydrogens come between 6 to 8 ppm, and aromatic hydrogens also come in the region of 6 to 8. Olefinic hydrogens come at a lower delta value here, and the aldehyde hydrogens and the acid hydrogens come at a higher delta value. Coupling constant is the distance between the gap. Coupling constant is a gap between the lines in the spectrum. So, you can take any one of the gap and measure the frequencies of the signal. That will be the coupling constant. Okay. Coupling constant tells you structural type of the molecule. In this particular case, the coupling constants are given here. Chemically equivalent protons will have the same chemical shift value, hence the homotopic and the anisotropic hydrogens in the organic molecules. Methane, if you take, all the 4 hydrogens are equivalent, right? So, it is a tetrahedral molecule. Ethane, methane, they all give a singlet in the NMR spectrum. Benzene, for example, will give a singlet in the NMR spectrum. Now, here this will give a singlet in the NMR spectrum because these 2 hydrogens are equivalent hydrogens. If we take naphthalene, there are 2 kinds of protons in the naphthalene, HA and HB. Because of the symmetry of the molecule, HA and HB, 4 protons each come into picture. If we take pyridine, HA, HB, HC, 3 types of protons are there. So, you should get 3 signals in the NMR spectrum. Here if you take, for example, HA, HB, HC, three types of protons are there. The intensity ratios are different. Watch out for the intensity ratio. This is 2 intensity, this is 4 intensity, B also is 4 intensity. If you take this molecule, phenanthrene molecule, there is only one plane of symmetry in this molecule. So as a result of that, you have HA, HB, HC, HD, HE. There are 5 types of protons are there in the phenanthrene molecule. So a well resolved spectrum, if you measure it, you will see the 5 spectrum, 5 line pattern in the NMR spectrum. Magnetically non-equivalent protons are the one where the magnetic environment is different for the different hydrogens. The 2 protons show spin-spin coupling, they have to be magnetically non-equivalent. They may be chemically equivalent or non-equivalent, but magnetically non-equivalent is a must. Now, diastereotopic hydrogens are chemically non-equivalent hydrogen. They are neither mirror images nor superimposable on top of each other. So, these 2 hydrogens, for example, are diastereotopic hydrogen in the molecule. There is a chiral center here. The chiral center is causing the diastereotopy here. Similarly, diastereotopic AB hydrogens are there, AB hydrogens are there. Here again AB hydrogens are there. So in this spectrum, some more examples of magnetically equivalent or non-equivalent hydrogens. The parameters one can measure in the NMR spectrum is the coupling, the chemical shift values of various protons you can measure. The coupling constant of various multiplets are measured. Relative ratios of the signals are measured. NMR can be a quantitative technique, provided you have an internal standard to measure it with and calibrate the spectrometer. Relative mole ratio of the components in a mixture can be obtained, and number of protons can be measured in each of the signals in pure samples. This is a spectrum of ethyl bromide. Ethyl bromide has how many types of hydrogens? 2 types of hydrogen, CH3 and CH2. The CH3 will split the CH2 into a quartet, and the CH2 will split the CH3 into a triplet. So you should see a triplet and a quartet. Can you see the triplet here? This is a triplet, 1:2:1 ratio intensity, Pascal triangle. This is a quartet, 1:3:1 intensity ratio. So 1:3:3:1, 1:2:1 are the ratios of the signals for the. This is propionamide. Propionamide has a NH2 hydrogens. NH2 hydrogens are special type of hydrogen in the NMR spectrum. Because nitrogen is a quadrupolar nuclei, they usually give broad signal. The NH2 signal comes around 6.5 or so as a broad signal. And here again, a triplet and a quartet is what is expected for the CH3, CH2. And you can see that. As you go along, you will get more and more complicated spectrum, you will see. This is a simpler spectrum. Benzene, benzoate. This is benzyl acetate is the compound, benzyl acetate. Benzyl acetate has a CH2 which is attached to oxygen. So that comes in this region, higher delta value. And CH3 comes in the region lower delta value for the. Here there are 4 hydrogens in the molecule. Integration ratio wise, if you take these hydrogens here, this compared to this hydrogen, this is a 4 hydrogen system. Cyclopropane dicarboxylate. Three isomers are possible: cis isomer, trans isomer, and geminal isomer. Which one of the isomer will have the simplest NMR spectrum? This is a fairly complex NMR spectrum. You have multiplets all over the place. Whereas, which one of the isomer do you think will have the simplest spectrum? Simplest spectrum means all the hydrogens have to be equivalent. Geminal one. Because geminal one has only one type of hydrogens in these two positions. So it will be a simplest spectrum. So that is not it. What about between these two? This will have a hydrogen here and a hydrogen here. They are equivalent hydrogen. And these two hydrogens will split the CH2 into a triplet. Right? Do you see a triplet in the spectrum? Do you see a triplet is further split into a doublet in this particular case? So triplet of a doublet is what you see here. Geminal is a A4 system. A4 means all the hydrogens are equivalent hydrogen. Vicinal cis. Three signals AM to AMX or ABC. Vicinal trans AB2, A2X2, two signals. Since there are three signals expected for this compound, this is a spectrum of the, this is a compound of the spectrum that is shown here, this particular. Here you see, for example, a complex spectrum. Complex spectrum, aldehyde hydrogen comes as a doublet because of the adjacent hydrogen. This is a multiplet you see here, for example. What do you see here? This is 1, 2, 3, 4. 1, 2, 3, 4. There are two quartets overlapping with each other.